Okay, you can start.
Okay, so we will start a new module in the complexity course. The next 5 to 6 lectures will be on this new topic, which is called interactive proofs. It's, you see, it will be an initial flight of fantasy, and eventually we'll relate it to very topics that we talked about. So the first 20 minutes or so of this lecture will actually be trying to motivate what is this new notion of interactive proofs and stuff. So to begin with, let's recall our notion of NP. So we wanted to prove something. So there was some theorem that we wanted to prove. Or rather, the verifier wanted to understand the truth of this theorem. So say X belongs to L. This could be a particular graph is 4 colorable. This could be this particular theorem is true. This particular Fermat's last theorem is true. One of these. So there was this verifier V. In particular, it was a deterministic Turing machine verifier. The verifier wanted to understand that this is true. And in case of NP, we were looking at things which the verifier is not capable of solving this problem themselves. They need more power. It was not a problem in P. If, for example, say SAT, satisfiability, or 3 colorability, problem like this. The verifier needed, so it said that if you give it an extra power, if you give it a proof, which the verifier does not care how the proof was fed to it or any such thing. That is, for every true theorem, there exists a proof which you can give to the verifier. And looking at this proof, the verifier proof pi, the verifier can be convinced that actually the theorem is true. But but if the theorem were false, there exists no such proof that convinces the verifier that this one. That is, there doesn't exist a short proof that convinces the verifier of the veracity of a false theorem. Every true theorem has a short and nice proof. This was what we defined NP to be. We want to take a slight twist to this model of computation. So that's sort of, so in this way in which you not only have access to the proof, but you actually also have access to the person who came up with the proof. For example, so in the few lectures ago, we saw variance, Sharpe completeness we did. So suppose you are not just seeing variance Sharpe completeness, the variant was actually out there writing out the proof of Sharpe completeness. There was actually a prover out there. Like, for instance, when Moses got his 10 commandments, not only were the 10 commandments actually given to him, there was God actually out there handing over the 10 commandments to him. Or when the Gita was being imparted to Arjuna, it's not just the text of the Gita, but actually there was this person out there who was imparting this one. Question, what we want to know is if you have access to this prover, and not just this proof, not just this piece of text, can I do more? Can I learn? So when I say I'm going to put myself in the shoes of the verifier for the rest of this lecture. I'm going to ask, so certainly with the help of a proof, I can do certain things more than which I could do without a proof. For example, with the help of a proof, I could possibly understand that this graph is 3 colorable. I might not have been able to come up with the 3 coloring of the graph, but I could use this proof. So the proof, I could use that proof to convince. I could not factorize a particular number, but somebody could actually give me the factorization and I could check that the factorization is correct. So in these cases, so having this proof written on a piece of paper actually helps me to understand a little more than what I could have done previously. But now we're going to ask a question. We're going to introduce the question. So suppose not only I have access to the proof, but I also have access to this prover, somebody who came up with the proof. Can we do more with the prover? Can we do? That's the question. Can I somehow now try to answer? So what I'm going to replace, so the question which I'm going to ask, this motivating question for us is, what if the verifier had access to the prover and not just the proof? So for instance, the setting is sort of this, there's a V, there's a deterministic verifier.
Prahladh, there is an instead of is.
Pardon?
What if instead of what is?
So you had a prover, or possibly a very powerful entity. So since there was Valiant out there, not only give you the proof of the Sharpie is complete, but he was also out there, or you're like Arjuna out in the battlefield, and there's a thing out there. What do? You do exactly what Arjuna does. You ask, Kim no Rajyena Govindam, Kim Bhoger Jivitena Va. You ask, what use is this kingdom? Of what use is war? Of what use? You start off, you initiate a conversation with the prover. You sort of ask Valiant why thought permanent was a candidate problem for being sharply heard. You initiate this sort of conversation. You sort of start off, let's ask. So I'm going to ask you a question. So previously there was just pi being given to you, the proof being given to you. But now you sort of ask questions. You can ask question 1, the prover answers, he gets answer 1, you can ask question 2, so 2, and so on. So you can sort of have an interaction with the prover. We'll have to formally define what this means, what does an interaction mean and all, but let's just do things very informally for now. See if we can actually do something out of it. Does it actually help you to have this interaction with the prover? Certainly if you're sort of your role model or something is out there, you just don't want to get the piece of text from them. You actually want to have a conversation with them, get more things out of them. Usually this is useful. And we would like to understand, is this really useful in some sense of, such as a word, can I actually get more out of having an interaction with the prover rather than just getting the proof? So what do you think? I haven't defined things formally, so everything is very informal. So suppose I had an interaction with the prover, will I be able to prove more things? Can I prove things? So we are going to look at everything from computational point of view. Am I going to be able to prove things, say, beyond NP with this? Can I do this? This is a sort of thing I want to ask. The question is, suppose I have access to such a prover, can I do more than what I could have done previously? What would your guess be? It seems as if certainly everything that you could do with a proof, you could also do with a prover. So it's at least as powerful, which is good. But the question is it more powerful? Does it give you more power? Do you get to understand the concept? Do you learn to do more with having access to this prover than with just the plain proof? Is this model sort of clear what's happening over here? It's a slightly non-standard model. You don't just have access to this proof, which is this string of text, but you actually have access to this prover. This is all-powerful other person who can think of it as a Turing machine, which can run all sorts of algorithms. There's no limitation on time, space for that Turing machine. It's an omnipotent Turing machine over there. It can do all sorts of things, possibly even compute the halting problem and all sorts of stuff. You're willing to have a conversation with this, can you do more? But the one thing about it is, just like in a proof, you don't trust the prover. You need to verify it. Like a proof, if somebody says this graph is 3-colorable, you don't trust it. You ask them for a proof. So if you have the access to such a prover, can you do more than what you have done?
So does Valiant does sort of the prover to one problem, to his theorem, and we are the sort of verifiers in that case. Right?
We are the sort of verifiers, yes. Yeah. I want to say, if the prover is really, really powerful, in the way I have set it up, you really can't do much, because the prover could say, this is going to be your first question. This will be my answer to your first question. Then this is going to be your next question. This is the answer to my answer. See, this is the whole transcript. I have written down the transcript. Go check it for yourself that this is the conversation you would have had with me, and end of story. So it's the same thing as if I give you a proof. The prover could, if he knew that the prover is so powerful, he could have actually known what's the conversation that you're going to have a priori. The prover could have just replaced themselves with just the transcript of the conversation. And the verifier, the deterministic verifier, goes ahead and checks that this transcript of the conversation is indeed the conversation that the verifier would have asked, and then checks if all the thing and I got it. So in that sense, this interaction really did not give the verifier more power. It could have been done in just the plain old NP language, in which the prover, instead of having the interaction, he just gives out writes down the transcript of the conversation out to the verifier, and the verifier just now goes and reads this transcript. Oh, I would have asked this question, and then the prover would have answered this question. Then I would have asked this next question, and then the prover would have answered the next question, and he reads the whole transcript. This is exactly the setting of a proof. There is no prover. There's no interaction back and forth. The prover just in one shot says, this is the entire transcript. This is the first question you would have asked, then I would have asked, given you this answer. Based on this question, you would ask me the subsequent question, then this is your answer. Because the prover can foresee things, he's going to ask you an entire sequence of questions, write down the whole transcript and say, go have this. So there's no need for an interaction of the prover. Do you follow this, what I'm stating over here? So I want to say in this setting, actually having access to this omnipotent prover is not really more powerful than having the proof, because he could have just written down the transcript of the conversation, of the interaction that we were going to have with the prover, and not wasted time talking to us. Could have just written this off. But the fact that the prover can do this depends on one key fact. And if you break that fact, one key assumption of the verifier, if you break that assumption, I want to claim that this is no longer true. And can you look at what the picture I've drawn and find out what is this assumption on the verifier that the prover can actually write down this transcript?
The questions, he knows the questions, right? If he can write down the transcript, then he knows, oh, these are the certain questions that he'll ask.
Yeah. So why does he know the question? Why does he know the questions? Because it's a deterministic verifier. He knows exactly what the first question is. And if he answers it, he knows based on this answer, what is the next question. The provers can certainly run the verifier themselves. So the one place, so question is, does the prover get to know the questions up front? Certainly he will get to know the questions up front if the verifier was deterministic, because the prover could run it themselves. But this is no longer true. That is, my question was, does interaction increase power of verifier? No, not really. However, I want to say, however, this is not true. Going back to Satyajit's question, if the verifier is randomized, the verifier is allowed to toss random coins, then the prover does not know what the question, because he needs to know what are the random coins also that the verifier tosses in order to find out the question. Of course, you could say he would, for every possible random coin, he will say this, if your random coin was this, if it came out heads, tails, tails, this would have been your question. I tell you this one. But notice that once you allow this, then there are too many potential questions and the transcript becomes explosively large. He can't write down a short transcript. The transcript he has to write for every possible choice of random coins. There is no short transcript. So this notion of the prover being compacted into the transcript is a feasible option only if the verifier is deterministic. If the verifier is randomized, the prover can't write down the entire transcript, all possible transcript, because all possible transcripts are way too many. He can't write a short transcript. So it seems as if when you interact with the prover and the verifier tosses random coins, you can do something. At least I don't know a priori that the verifier can capture, that you can capture everything by just the prover writing down. Satyajit, you had a question?
So the first thing we knew, okay, Q1, Q2, Q3 is sort of the sequence of questions. Now, if you say that the verifier is random, that means he can ask Q3 at the beginning, then Q5, then Q8 or something.
No, not just that. Even the first question itself, first question not only depends on the input X. So X is a common input they both have. They both are trying to prove this. The heart of it, they are trying to prove this theorem. They're proving the particular graph is, say, three-colorable or some nonsense like that. They want to prove that. They both have this, and the verifier could now toss some more. So Q1 is not just a function of X. Q1 is function of both of X and the random coins which the verifier tosses.
Okay.
So Q1 itself has, there are several possible Q1s. Q1 is not a fixed. So Q1 is not a fixed. This one, Q1 itself, the question you could ask could be it could be a randomized question based on the random coins. And now there is no one short transcript, because the prover, if he has to write a transcript, he has to write a transcript for every possible random points, and the verifier is crossing polynomially many random points. These are just way too many. The transcript is way too much. At least in this case, so what we want to say is, it's the whole, this notion of moving from a proof to a prover was trying to show that it's sort of nicer to have an interaction with the prover. But if the verifier was deterministic, this interaction really did not give you more power. Verifier is, so we'll allow the verifier to be randomized. So now we're going to go to a model. I'm still not yet defined a model in which the verifier is verifier is randomized. And is allowed to have an interaction with this powerful prover. With a powerful prover. And we want to know, can you do things which you cannot do otherwise, which we did not know how to do otherwise. I'll have to define what this model is formally. I'll do it in about 5-10 minutes. But we'll start off with an example. We'll actually show there is something which previously I could not do in the usual NP setting, but which I can do when I allow for randomness and the ability to have this conversation with the prover. Okay. Please, informally is a thing clear. Formally, I will define it shortly. Informally, let's go to this. Yeah.
Yeah, so I mean, in this case, when you use random points, the transcript, if the prover wants to send a one-shot transcript, that is very long.
Yes.
But yet the verifier only accesses polynomially many bits of that transcript.
Yes.
So if I ask for a model where the prover is allowed to send a long transcript, but the verifier only gets to access some polynomially many bits, as many as.
But that's essentially having like an interaction with the prover, no?
So yeah, I'm not sure. Is it the same, exactly the same? Because aren't you, like in some sense, you have tied the prover to commit to the long transcript. Like he cannot change his answer after looking at Q1.
Yeah, but I agree. It seems as if it's more powerful having the prover this way. But on the other hand, because he's going, the transcript is itself is written in an interactive format. It's written, if you, let's do question 1, then question 2, then randomness 1, randomness 2. The prover is not committing to anything over there. It's exactly this would be exactly the same thing as having an interaction with the prover. I don't think there's any difference in the two models.
Okay.
Okay. I don't think you can check this up. There's no difference in the two models. That is, what you're stating is now the transcript, the prover is the proof going to be given to you as an exponentially long proof, but based on the random coins, the verifier will look at only a polynomial sized part of the proof. So this is the same for me as having an interaction with the with a powerful prover. Okay. Anyway, I haven't defined anything formally, so it is feasible that there might be something that escapes this definition. But let's start off with one toy example, which we're going to work with. Actually, it's not a toy example, it's a big example. It's what's graph non-isomorphism. Then GNI. You're given two pairs of graphs, G1, G2, and G0 is not isomorphic to G1. These are two undirected graphs. Notice that GI, the complement of GNI is GI, and this is an NP. Because if two graphs are isomorphic, I can give you a short proof that the graphs are isomorphic. If two graphs are non-isomorphic, a priori, I don't see an easy way to give you a short proof that convinces you that the two graphs are non-isomorphic. Okay, so the only way I see how to do it is go over all possible isomorphisms, mappings between the two things, and show that each one of them is not an isomorphism. And there are n factorial many, potentially n factorial many mappings between the two graphs. Assume the two graphs are of the same size, same set, then the n factorial, that's not short in any sense of the word. But what we'll show is, surprisingly, this particular problem does if you're allowed to have a conversation with this prover, and if you're allowed to toss coins, then we can actually do something quite remarkable. We can have a short conversation with the prover, at the end of which we can be convinced that the two graphs are non-isomorphic. And this is sort of going to be based out of something which we have done, which we are quite familiar with. So suppose I can't distinguish Coke and Pepsi. There are two drinks, and I say they're the same. They're actually the same drink, which is two different companies are constantly. I can't distinguish. And you claim that actually you can distinguish Coke and Pepsi. What's one? So I can't. When I drink them, they taste the same to me. And you claim this bottle has Coke to it, this bottle has Pepsi to it. I can't just tell the two things apart. What's one way for me to test?
You tell me which is which. You ask me which is which.
Of course, you already told me this is Coke, this is Pepsi. So this one. So what I could do is I just go without your knowledge, pour one of them into a glass. You do not know which one I poured. Then give it to you and ask you to tell me which one had I poured. Did I pour Coke into it or Pepsi into it? And if you were actually able to distinguish, you will be able to tell me which one I poured. This one. If not, you have a 50-50 chance. You will just this one. If they were indistinguishable, there's no way you will be able to tell apart. If they were actually distinguished, and we're going to do exactly the same idea over here. So we're going to have this. So G0 and G1 are something both the verifier and the prover have access to. It's a common input given to them. And the prover wants to convince the verifier that actually G0 and G1 are non-isomorphic graphs. That's the goal of the prover. What will the verifier do? We're going to do exactly the same as before. You're going to pick one of the two graphs at random, just like you pick Coke or Pepsi. So I'm going to pick one of the two graphs at random. And I want to send over that graph. So I'm going to send GB to the prover. But possibly the graph G0 and G1 were written in such a way. B is just a bit.
Oh, okay, sorry.
So I'm either going to set GB across. But the point is, if you do this, it's possibly that the way the first graph was written and the way the second graph, I assume they were given an adjacency matrix representation. It might be that the first graph is written in a slightly different fashion from the second graph, and hence the prover will be able to tell, looking at whether I'm sending the adjacency matrix of the first graph or the second graph, which of the two graphs I actually sent. That is, if I had given Coke and Pepsi in the original bottles itself, you can tell me that which was this one. So what I do is I want to do some more mixing of it. So what I will do is I'll pick a random permutation of the vertices. Let's assume n is equal to size of VG0, which is also size of VG1. By the way, if the two vertices are of different size sets, you can already tell they are non-isomorphic. So the only hard case is when the two vertex sets are of the same size. And then you construct H, which is this permutation of GB, and you send H across to the prover. So H is just a permuted copy of one of the two random graphs. And the prover is going to return a C, and you accept if B equals C. If this bit were actually, the prover is able to tell clearly the graph that you sent, is it the first graph or the second graph? If the two graphs were actually non-isomorphic, the prover will be able to do this always. If the graphs are isomorphic, then the graph with H which you sent across might just as well be a copy of G0 or G1. So formally, this is what is happening. If G1 is non-isomorphic to G2, then the correct prover P, when this verifier answers, has a conversation with this correct prover on this G0 and G1, it will cause him to accept, will be with probability 1. Will always accept. And if G0 but on the other hand, if G0 were isomorphic to G1, then no matter which prover you work with, if I have this conversation, this verifier has this conversation with this, so no matter which prover I work with, notice that this is always half. Because H is going to be H could either be G0 or G1. It's equally likely to be G0 or G1. So C could, there's hardly any chance so B is a random bit which the prover does not know. So no matter what C the prover returns, the probability that C equals B will be just a half. Are people with me on this? This is exactly the Coke versus
I
Pepsi.
didn't understand what is C.
C is just prover telling you, is it the first graph or second? C is a bit. Prover is telling me.
You should reject if B is equal to.
This is just.
Oh yeah, you should accept if B is equal to C. Yeah.
You accept if B equals C. Yeah. This is just the Coke versus Pepsi example written for graph non-isomorphism.
This sigma is chosen randomly, right?
Yeah, sigma is chosen randomly. So there are two randomness going on over here. One is this, and the other is this. So there are two things. There's randomness going on over there. There's an interaction going on over here. These are two senses in which it's different from the usual NP proof. The usual NP proof, the verifier is deterministic. It doesn't toss any random points. Here, the verifier is randomized. It is tossing random points. And furthermore, there is a back and forth interaction. There's a question being posed, which is H, and there's an answer being obtained, which is C. So it is an interaction. It's different from the usual. The usual proof, there's just what's one-sided from the prover. The prover sends something across, and that's the end of story. Here you're going back and forth. There's just one question and then an answer. And in fact, the prover is just returning a bit. I claim that this already tells you that you can do something in this model which I previously did not know how to do. So if I had access to such a omnipotent prover, I can use that prover to have a short conversation with the prover and convince myself that these two graphs were non-isomorphic. Previously, there was nothing I could do in a short time and be convinced that the two graphs are not isomorphic. Anything in which I need to be convinced that the two graphs are non-isomorphic, I needed to look at an exponentially long string. Here, just because I'm allowed to have a conversation and I'm allowed to toss random points, somehow suddenly my life becomes much simpler. Because I have access to this prover who's omnipotent and I'm able to toss coins, I'm able to, using this prover, whom I don't trust, I'm able to find out if these two graphs are isomorphic, graphs are non-isomorphic. And people
I didn't understand when G0 is isomorphic to G1, why is the probability that you accept is equal to half?
So when G0 equals G1, H might as well be from G0 or G1. It really does not matter. H is just a random copy of the same graph. So B is now just a random bit. H is not giving you any information of G0 or G1. B is completely a random bit. In the case when G0 and G1 are the same. If it's the same graph, H as well looks like G0 as G1. So looking at H from the prover's perspective, B is a random bit, which can equally likely take 0 or 1. Therefore, no matter what value the prover gives you C, this bit is hidden from the prover. So that probability that the C is equal to B will happen with probability half.
Yeah.
Okay. Okay, so that's the model. So let's actually now, so already we've seen that this model, so I'm going to define this new notion called interactive proofs. IP.
So these interactive proofs somehow seem like it's in the RP, right?
No, certainly it is contained in RP also.
Yeah.
RP is in it. In fact, all of BPP is in it.
It's not contained in RP. It contains RP.
It contains RP.
If this interactive proof is a subset of RP.
No, it's not, right? Because graph non-isomorphism, we don't know of any randomized process to figure out whether two graphs are non-isomorphic.
So from this probabilistic thing.
What probabilistic thing?
If G0 G1 belongs to this G0 G1 belongs to this language, then you have a
No. Probabilistic thing, there is no notion of a prover there. Everything is done with the help of the verifier himself in RP or BPP. Here you're harnessing the power of this additional prover. You're using the fact that the prover can tell things apart.
Yeah.
So this one. But whatever, I'm going to define this IP class shortly. And IP, however I define it, graph non-isomorphism is contained in IP, and we don't know if GNI is in NP. This is a question. So IP60 seems to contain something which is not just NP, it's slightly more powerful than NP. Okay, so let's.
Prahladh, in other thing, if the prover had written a really long transcript where I could probe it, this was pretty easy to do, right? I could have just, for whatever random permutation or etc. Okay, I can go and ask for what edge is not mapped.
Yeah. No. What do you mean?
Yeah, the number of non-isomorphisms I do not know.
Okay. No. So there are two things. There are two models. If you're allowed to write a very long transcript, certainly I can do it because you put every possible map. If the verifier is allowed to read the entire long transcript, which is exponentially long, then certainly we can do it. But suppose we go to your model of this one, in which the verifier is a long transcript, but the verifier is only allowed to read a polynomial part of the long transcript. Then this is the exact same protocol which we'll follow.
Yeah.
Okay, Satyajit, you also had a question. Okay. So now let's actually try to find out how am I going to formally define this thing. So let's actually be a little pedantic. Let's recall the formal definition of NP and see how we are going to modify it in this setting. So recall definition of NP. So NP, once again, remember, is this setting in which X is in L, there's a verifier, a deterministic verifier, and the prover, all the purpose of the prover is sending this one proof across. The verifier is checking if P of X pi equals 1. Let's call it accept reject. So more formally, we'll say that L is in NP if the following things were true. If there exists a verifier V with the following properties. And we'll modify all these properties to define the first property we want is efficiency of the verifier. V is a polytime machine. It's a polytime computable.
Also, pi isn't too long.
Huh?
Pi isn't too long.
Sorry, I didn't.
Pi
comes from the fact that V is polytime, because if pi is too long, certain parts of pi we will not just be able to read it. Then what is called completeness is if X is in the language, then there exists some proof pi such that V of X pi is equal to accept. That is, for every string in the language, you have this. And soundness is for X not in the language. No matter which proof you give me, you cannot convince me to accept. You cannot. This was how we defined NP. We're going to take the same approach to now define IP, except now we have to model interaction. So we want to extend this definition.
Instead of there exists pi, it will be there exists some few questions.
Yeah, so we could do a few questions. So what we will do is we will model And for interactive proof, we are going to the verifier takes two inputs now. It's going to take. So we have to model how do we model the verifier? Its inputs are firstly X, the original input. It's going to toss some random points. So R, it has some randomness. It's a randomness. And because it's going to be interactive, the way we are going to look at the verifier is not the way we're going to come up with the verifier is it looks at the input, the random points, and looks at the transcript so far and decides whether it has to ask a next question or whether it's going to accept or reject. So we can think of the verifier as something called the next message function. The verifier looks at the input, the randomness, and the transcript so far and decides whether he wants to ask the next question or whether the verifier wants to accept or reject, or this transcript is already a response. So the verifier is modeled as a next message function. So V, so it's a next message function V, which maps X, R, and tau, the transcript. It maps it to the next message or the question. You can either call it question, next message, or an accept reject. And the prover is the same thing, except the prover does not have this randomness. The prover has the input X, the transcript, and he returns the next message. So the way I'm going to view this is there's a verifier, there's a prover, they have a common this one. The verifier tosses a couple of random points, or based on this, he runs at this one, asks the first question. The first question, M1. M1 is V of X, R, and the empty transcript so far. And the prover then returns an answer. Then the M2 is V of X, R, M1, A1. Based on that, he gets M2, asks this. The prover returns A2. Finds M3 based on V, X, the transcript so far, M1, M2, A1, A2, and keeps on going. At some point, he decides to either accept or reject. Okay. And we'll now say L is in IP, short for interactive proof. If the following, if there exists a verifier V, a verifier next. So basically, verifier is just a next message function. V, and this is also randomized, so it takes two types of inputs, such that the following are true. One, as before, efficiency. V runs in time, poly in the length of the original input. Therefore, all the randomness it uses, all the transcripts it sees, everything have to be polynomial in the length of the original input. That's efficiency. But never does it have to do anything more than this one. Two, completeness. For every X in the language, there exists a prover P, such that when this verifier next message function interacts with the prover on both the points X and R, so the random points is only over R, this will cause it to accept, happens with probability greater than, say, 2/3. And soundness. Same thing. If X is not in the language, then for all provers, not just, no matter which prover you give me, so let's call every prover, no prover should be able to convince me with probability more than 1/3. Okay. So this is how I'm going to model the interactive randomized version of NP, which we call interactive proofs.
So could you just go up a bit?
Yeah. Oh.
Yeah. What does there exist a prover here means? Like there exists these M1, M2.
No. So what does there exist prover? So I was a bit sloppy about that. So let's say what there exist prover means. So what does a prover mean? So a prover is also a next message function. The prover is also a next message function. It's also this one, except we don't put any efficiency requirements on the prover. The prover can run as, it's just some function that takes, given the input and the transcript, outputs this one. It could be randomized, it could be deterministic. Let's for now assume it's deterministic. It doesn't matter, because if it's randomized, it could just run over all random points, find the best answer, and then return it. So there's no point, because it's all part, we're not putting any efficiency restrictions. The prover might as well assume the prover is deterministic. So when I say there exists a prover, the prover is also a similar next message function. The next message function.
So that graph non-isomorphism algorithm, does it fit into this?
Yeah, let's go to that. However, with no efficiency restrictions.
Then you can say it's like some oracle, right?
An oracle, but yeah, you can say it's like some oracle.
Because we don't
but
have
the point you don't. The point is it's an oracle, but it's an oracle whom you don't trust. Usually, an oracle is something you trust. Here is an oracle, like here you don't trust the oracle.
To verify it again.
You will need to verify. Just like in the case of NP, you don't believe the proof. You will want to check that the proof is correct. Here also, it's an oracle. It's an oracle, and you want to say in the yes case there is one oracle which will convince you that it's correct. In no case, no matter which oracle you give to me, even a cheating oracle you give to me, I will not be convinced. Okay, so let's go to Vinod's question. Let's go to this one. Let's look at the next message function of this one. What's the next message function? This is just a 2-round protocol. Verifier asks one question, prover answers. What's the randomness needed? The randomness needed to pick a bit B and a random permutation. There are n factorial permutations. So log of n factorial bits of random coins need to be tossed. That's a polynomial amount of random coins in the input of the graph. So the verifier can do this. So that's this one. So based on that, it decides the first question, sends it across. The prover is now an all-powerful prover. It looks at H, it stares at H and G0, it stares at H and G1, finds which of the two things it's isomorphic to. This is not something which a polynomial time person, I do not know how to do it, but the prover can afford to do this. So the prover is this next message function. He looks at H, G0, G1, finds out does H look like G0 or H look like G1. And if it looks like GI, it looks like GC, it sends the C such that H looks like GC. It sends that C across. And then the verifier, based on this, just checks if B equals C. So this exactly fits into the model we talked about. And in the yes case, you accept if they're non-isomorphic, there is one prover which will cause you to accept with probability 1. In the no case, okay, it's not 1/3 as I said there, it is half. In that sense, it differs.
Yeah, that's what I wanted to know.
Yeah, so
is that okay?
It's half, but you can just repeat this constant number of times. You can just repeat it and make the 2/3 go close to 1 and the 1/3 goes close to 0. You can just repeat the whole thing again and again. So half can be made 1/4 if you just do it twice. You do a 2-round thing. You send this, You return C. Now you pick another H prime in the exact same fashion. What's the probability that in both cases you could have got correct? You could have got fooled. It will be 1/4. Okay. So GNI fits in this model of IP. So IP. So all I want to say, I'm going to make several remarks on it. So let's look at several remarks on the definition of IP. So certainly, I think NP is certainly contained in IP. The verifier is not randomized at all. The prover is just, verifier does have no first message. The prover just sends the first message across and that's it. BPP is also in IP, in which there is no prover at all. The verifier tosses random coins. Based on that random coins already decides the answer. It doesn't ask a prover the question at all. That's BPP. So IP sort of captures both NP and BPP, does it? But now, question is, does it have more things than it? We already saw that it has graph non-isomorphism sitting inside it, which is something which I don't know is in NP, but we saw a very efficient two-prover interactive proof for two-round interactive proof for IP, for a graph non-isomorphism. Okay. So these are two things. I want to say the next one will be exactly what Vinod said. The error in definition is 1/3, but can be driven, but can be reduced to, say, 1/3 power m, reduced to exponentially small in m, just by repeating the above protocol. Sequentially order m times. So once again, just like in the case of BPP, these 1/3, 2/3 are not going to matter. We can push them to any number exponentially close to 0 and 1 if you just allow the protocol to increase by a polynomial factor. Okay. That should be, this is not hard. You can do another type of repetition, an alternate repetition, in which an alternate repetition can be performed by asking questions in parallel. So it's surprising that this also works, but this will require a proof, and we will not assume this. That is, so in the case of graph non-isomorphism, what do I mean by parallel? You pick you pick B1, B. So what's the sequence? You do the first. What was sequence means? Sequence means you do this protocol, you do this whole protocol. At the end of this, you toss another coin B prime, toss another sigma prime, find out H prime equals sigma prime of G B prime, send H prime, get a C prime and do it. That's doing the whole thing in sequence. In parallel means I do B and B prime, I pick them both in parallel. Then I pick a sigma and C prime. And in this round, I said H and H prime together. I don't just send H, I send H prime together. And the prover answers for C and C prime together. So the total length of the transcripts all remain unchanged, but the number of rounds is as before. It doesn't increase based on repetition. You can show that this also works, but this is something we will not assume that is can be performed. This also works, also reduces error, but this requires a proof. And it's good to know this. We will not prove it in class. And this is sometimes
when you repeat the algorithm, you accept if at least one of the repetitions accept, or
graph non-isomorphism case, you could have done that because it was one-sided. But in general, if it is not, you accept if the majority of them accept it. If it's like BPP sort of setting.
So again, Chernoff bound will
have Chernoff. Yeah, so it's not fully correct that you don't need Chernoff for this lecture. Yeah, we'll use Chernoff. Yeah. Okay. Another thing. So there's something called, in the yes case, there's a correct prover. In the no case, you want to work even against the cheating prover, the dishonest prover. So like an NP, even against a purported proof you wanted to work against. So here also you could say the same thing. The honest prover. What is the correct prover? They use different terms for it. In the S case, actually any prover, why the honest prover? The prover. Right now we define the prover to be, the prover can be probabilistic, in itself randomized. The way the definition did not allow for this, but I want to say the prover can be deterministic, and the reason is, but this does not give the prover any extra power. Additional power. As the prover can find out which random coins maximizes the probability of accepting and use that particular random coin. The prover has an infinite amount of time to do this. The prover can do it. Sometimes we will find out this one. So let's leave it at that. The other, I want to make several observations. Some of these things which we will be proving as the lectures go, as subsequent lectures, is what I'm going to call private versus public coins. So let's look at this particular protocol for graph non-isomorphism. The question of what private and public coins is, does the verifier reveal which coins he is using to the prover or not? If he does not, if the verifier is not revealing it, they are called private coins. If the verifier is revealing them, they are called public coins. What's the graph non-isomorphism protocol? Is it a private coins or is it public coins? So in the graph non-isomorphism protocol, suppose the verifier, in addition to giving H, it released out what B and sigma were. Then does the protocol stand as it is?
I didn't quite get the definitions of public and private thing.
So I haven't defined them formally. So let's look at this particular example, graph non-isomorphism. These are the random coins of the verifier. Based on the random coins, the verifier is computing this function H and he's revealing only H to the prover. But suppose the random coins that he picked up, he revealed them also. Then it's called public coins. Then everybody knows the coins. This is called public coins. It is whenever he finds an answer, he also tells these are the coins that caused me to accept, that caused me to come up with this question. I'm revealing. Those are called public coins. If he's going to keep the coins hidden and not reveal it, those are called private coins. These are the two different models. Notice that in this protocol, it was important that the verifier the coins are private. Because if the verifier reveal the randomness, there's no problem. The prover has to give C equal to B. If he knew B upfront, he's going to give you the same C. It was important that the verifier was this one. So all I'm going to claim, I'm not defining this formally. So private is a thing in which an IP protocol in which the verifier does not, and it's important, it does not reveal their randomness.
So suppose it in the above example it did tell the sigma and the b, then would there be a change in the probabilities on the right hand side?
Yes, once you state that, then the cheating prover can completely cheat. No, he has to give a C such that C equals B. He knows B. He will always give the C such that C equals B.
Yeah. So then when G0 is equal to G1, in that case, it will be accepted with probability 1.
Yeah, there is a cheating prover that causes you to accept. It was important for the soundness of the graph non-isomorphism protocol that the protocols was a private coins protocol. If it was a public coins, the soundness breaks down. The soundness relied on the assumption that the coins were not, the verifier did not reveal the coins to the prover. So public coins is exactly in which the verifier reveals the coins. Okay. And the graph, if you look at the graph non-isomorphism protocol, if you stare at it, this one, stare at it for a while, you realize, actually you don't for a while, the very definition of the protocol, the soundness of the protocol relied on the fact it was a private coins protocol. If it was public coins, the soundness just breaks away. It won't be a protocol at all. It won't have one of the properties of the defining features of the protocol, which is soundness, will break away if it were a public coins protocol. So the surprising thing which you, yeah, go ahead.
Could you tell an example of this IP where here we only had one question and one answer, right? We only sent an H and that guy gave you the C. Can you give an example where we have a series of conversations?
So one thing we already saw this in answer to Vinod's question, this IP protocol had only a soundness of half. If you wanted to get soundness 1/4 smaller than it, you repeated it twice. Already there were 2 questions there. But we'll see more involved by the end of this lecture or even next lecture. We'll already see in fact, we will see an IP protocol in which there's not just 1 or 2 rounds, there actually be a polynomially many rounds. The question answers will go polynomially long before you finally, the verifier decides to accept or reject. Okay, we'll see this shortly. But the funny thing, or the surprising thing over here is, surprisingly for every language that has a private coins IP protocol, there is a private coins IP, there is an equivalent public coins. This might seem shocking, and in fact we will do this. In fact, I won't prove this theorem in its full generality. At least for the case of graph non-isomorphism, we will give an alternate protocol which is fully public coins and still has this feature. It will be a public coin protocol at the end of which the verifier reveals the randomness. It won't be this protocol, it will modify the protocol, at the end of which the verifier reveals the randomness at every round, and yet it will be convinced that the 2 graphs are non-isomorphic at the end of the protocol. Okay. I'm just spending a lot of time on this definition, these things, because this IP is is not something which we have usually defined. The next thing I want to ask is, what about perfect completeness? That is, in the yes case, can you make this one? And so I defined it both in the yes and the no. In the yes case, the answer was 2/3, and the no case, the answer was at most 1/3. If in the yes case this answer was 1, it's called perfect completeness. Graph non-isomorphism, the protocol I gave, had a perfect completeness protocol. And what we will show, actually not what we will show, it will be in your 5th problem set, is that any IP protocol actually can be converted to one which has perfect completeness. So any IP protocol can be converted to one with perfect completeness. And the proof will be similar to the proof that BPP is in sigma 2p. Next thing I want to ask is, what about perfect soundness? Can I make it the other direction? Can I make the 1/3 drive it down to 0?
Could you just go back to the perfect soundness definition?
Perfect completeness definition or soundness? This one?
Okay, so you can drive it down to 0.
Yeah, drive it down to 0.
Okay.
Can I drive 1/3 down to 0? That's the question over here.
So then after applying both perfect completeness and perfect soundness, can you do both, like drive it down to 1 on one side and then drive this down to 0 on the other side?
Yeah. So let's ask that. I didn't answer this question. That question. So perfect. This one was where the question here was. Question was, can 2/3 be increased to 1? And the question here is, can 1/3 be reduced to 0? Can you drive the soundness error from 1/3 to 0? What's your... So the earlier one, I didn't show you how to do it. It will be a problem. It's a non-trivial problem, the proof, but it is something that can be done, and it's similar to the proof that BPP is in sigma 2p. You can show that you can drive 2/3 to 1/3, 2/3 to 1 all the time. Question is, can you drive 0? Can you drive 1/3 to 0?
You can repeat it like how many times?
You can make it as close to 0 as possible. That's true.
Yeah.
Question is, can you make it 0? And the answer to this is possibly no. Since suppose you were able to make it 0, then in the yes case, the prover can just send the random points that causes the verifier to accept. You can remove the randomness from the whole, possibly no, then can make the verifier deterministic by the prover just sending the random coins that cause the verifier to accept in the S case. So all I want to say is perfect soundness IP is the same as deterministic IP, which we know is NP. So if IP is actually more powerful than NP, you don't expect it to have perfect soundness. In particular, if graph non-isomorphism was not in NP, we don't expect that half can be driven down to 0. You can make it very small, but you cannot make it 0. Is this, do people follow what I said over here? Any questions on this? Or?
Just didn't get the part about sending the random
No.
count.
So what does it mean? So suppose you could drive the randomness to 0. Suppose there existed a perfectly sound protocol, so a protocol with perfect soundness. In other words, the soundness was 0, but it was a randomized protocol. Now I want to claim this protocol, I can eliminate the randomness completely by doing the following. In the yes case, the verifier does not toss any random coins. The prover says, you would have tossed this random coins, then you would have asked me these questions and this one, and I would have answered this way, and these are the random coins. Now, the moment the prover's verifier sees there is one random coins that is causing it to accept, he knows he has to accept, because in the no case, every random coins causes it to reject. So even if he sees one random coin that causes it to accept, so the prover, as part of his answer message, so the verifier does not toss any random coins. The verifier just waits and asks, is there a random coin that would have caused me to accept? And the prover says, yes, this random coins, and then will be our conversation. Henceforth, you can read all of this. So if it was perfectly sound IP, I want to claim it just collapses to NP.
Okay,
because
the prover will give the transcript beforehand.
Can give just that one transcript corresponding to this random coins which accepts. And the moment the verifier looks at this, he knows, oh, this one random coins accept. Therefore, this has to be an S instance. It cannot be a no instance, because a no instance, every random coin has to reject. So this is so if there was a perfectly sound an IP protocol with perfect soundness, then it has to be an honest to God NP thing. So if we believe IP is different from NP, this cannot happen. For instance, if you believe graph non-isomorphism is not in NP, there's no way in hell that protocol you can drive the soundness from half all the way to 0. You can make half to anything close to 0, but not 0. Okay. Okay. Any further questions? These are the remarks. So an IP. So we're going to talk about some parameters. An IP protocol. So usually this is written as L is an IP. But sometimes we want to specify a little more. We want to say the number of rounds. We want to tell what's the number of rounds. We want to say if it's public coins or private coins. We want to tell these extra features. So then we'll add in this one. Suppose the public versus private coins. So typically, if it's just private coins, we'll say L is an IP. But suppose furthermore, you actually had a public coins protocol. It's customary to call it L as an AM. That is, public coins IP is called AM, and AM is short for Arthur Merlin. We'll come to why this is this. So these are Arthur Merlin proof systems. These are just public coin IP protocols. So instead of saying public coins IP, I will just say the Arthur Merlin protocols. So usually this is said IP poly to say that the number of rounds are poly. AM poly to say. So actually I should have put this. This is the second one I wanted to do. Usually you also put the number of rounds. So you say if it's a K round protocol, you say L is in IP to the K. And IP is basically IP to the poly. You allow polynomially many rounds of protocol because the transcript can be polynomially long. Okay. Yeah, just one thing, but AM does not refer to AM poly. AM for some weird reasons refers to. So when you say AM, this is notation. The various, for historic reasons, you have all such notations. When you write AM, you'll always specify the number of rounds. When you specify IP, if you don't specify the number of rounds, it is polynomial. Otherwise, you explicitly specify the number of rounds. If it's a 2-round protocol, you specify 2. If it's 3-round protocol, you specify 3. AM in a public coins protocol, you'll always specify the number of rounds. So if it's polynomial, you specify polynomial. So in an AM protocol, In AM, we'll always specify the number of rounds. Okay. Any questions?
And these notations are just to distinguish between private and public coin protocols, right?
Yes, these notations is just
because each private coin protocol has a public coin equivalent also. So
yeah, it has a public coins equivalent also. So everything is actually in AM poly. Everything is in AM poly, but we will use this notation will be useful for us. So what I will try to do with the remaining about 14 minutes or so. So far we have saw graph non-isomorphism is not an, this has an IP protocol. In fact, it's in, so in fact, what have we seen? We have seen that graph non-isomorphism, example, GNI is in IP1. It's a one round protocol. By the way, this round also, what does a round mean? Does it mean back and forth, or is it just, is each question a round? I don't think there is, it's standardized. For me, a round is a back and forth is what I will call a round. Some people say this is actually IP2 because there are two questions going. There's no standard thing for it. As long as you are consistent in what you're writing, that's good enough. What we'll now see, we'll start, I won't finish it, this one. We'll actually show that public coins IP is extremely powerful. It can solve not just graph non-isomorphism, it can actually solve the permanent. So it can solve, the permanent means because of Toda's theorem, it can solve the entire hierarchy. Okay, so what we will do next, I'll just start it now. We'll give a public coins protocol, public coins IP, and this is AM protocol for computing the permanent. And this will really display the full power of IP. IP is the interactive proofs. Okay, graph non-isomorphism also already showed you that you could do something which is not. It says by having a short conversation with the prover, you can actually compute something which was way, way beyond our capacity previous. Okay. So let's get started on this. So A is the matrix. So A is a matrix Aij. So I equals 1 to, these are going from 1 to n. And just to be this one, I'm not going to think of this over matrices over the integers. I'm going to think of it over some finite field. We can move to this, but it will be convenient for me. So each Aij is in some f, which is a finite field. And we'll also assume that the size of the field is large enough, let's say larger than 2n cubed. The field is large enough compared to the size of the matrix. And the language which I want to compute is this permanent f is so I give you the field, I give you A, and I give you alpha. F is a finite field. And A is a, and I also give you say n. F n A alpha. A is an n by n matrix. That is, A is in f of n cross n, and the permanent of A equals alpha. That's the language. So I give you this. I want to find out if the permanent is this particular number or not. We'll give a protocol to compute this. Okay. So the next 5 minutes or so, I'll give you a protocol, and you have to. I'll give you a randomized protocol that does it, and you have to tell me what's wrong with this protocol. Actually, it just egregiously failed to compute. BNI, interactive proof protocol. But you have to tell me what is wrong. So let's recall the permanent definition. The permanent of a matrix A was the sum over all permutations P of this number, Ai, sigma I going from 1 to n. And this, we notice there's a downward self-reducibility. You could write this as I going from 1 to n, A1I, permanent of the matrix A1I, where A1I refers to the n-1 by n-1 matrix.
The first and the ith column removed.
By removing the first row and ith column, or the other way around?
First row, ith column.
First row and the ith column. Okay. So we are now going to come up with a candidate IP protocol using this downward self-reducibility feature of the permanent. So I'm just going to give A and alpha. F is fixed. F and N are fixed. This guy, A and alpha. So there's the verifier. There's the prover. They both get as inputs this. And the prover wants to convince the permanent of this matrix A is actually equal to alpha. He wants to have a short conversation. So what does the verifier want to do? The prover first, it's actually here the prover, this one, the prover begins on this one. Prover computes numbers alpha 1 to alpha n, each such that alpha I is the permanent of A1I. He computes these n numbers and he sends across these n numbers to the prover. The prover, first thing, what should he check? The prover should check if alpha is actually equal to summation I going from 1 to n, A1I into alpha I. Needs to do this check. But now it further needs to find out, are these alpha i's correct? That is, assuming what it has done is, assuming the alpha i's are correct, alpha is correct. That's what it has checked. It needs to check if the alpha i's are correct.
And again, it will check if A1I is in the A1I, alpha I is in the language.
Yeah, so it just
inductively summoned.
Check. So it's going to sort of just pick, this is going to be the randomness. It's going to pick a random 1 to n and just send this I, which is exactly what this is saying. So now the problem has reduced to A1I alpha I. So you reduced the problem to a n-1 by n-1 setting to check if perm A1I equals alpha I. And suppose we can do that. Suppose we had a protocol for n-1 matrices. You do that, and then you do that, you run that protocol, finish it off. You do the same thing. Now, once again, for that protocol, you split it up. You write A1i itself as is a sum over n-2 protocols. The prover sends all those permanent values. The verifier checks if that sum is correct, then picks one of them at random, sends it across. And this is the entire.
The randomization, like it does the random process only after alpha is equal to that, right?
Yeah, because if it's not, it does not. So yeah, one thing is the randomness is not chosen upfront. The randomness is chosen round by round. For each question, it picks up the randomness needed for that round. This is the way I'm doing it. Is this, firstly, is this a, so this is certainly, let's look at, is it a protocol? Is it an IP protocol? It's certainly an efficient protocol because everything the verifier is doing is efficient. There's nothing the verifier is doing which is inefficient. Notice it is n rounds. This is answers Satyajit's question. Beginning, is there a thing in which there's more than constant number of rounds? This will actually go for n rounds, 2n rounds the way I defined it. The prover gives, the verifier answers. The prover gives, the verifier answers. It goes all the way till you reduce to a 1 by 1 thing, in which case the verifier need not further subreduce the problem. So it's certainly efficient. It's also complete. If the permanent was actually equal to alpha, the prover can completely answer honestly and cause the verifier to accept with probability 1. The question is it sound? Is this sound? So let's look at, so I want to say, well, the question which I want to ask is this a valid IP protocol? I want to say efficiency is true, completeness is true, soundness is what I want to ask. That is basically, suppose perm A, this is the no case. Perm A is actually not equal to alpha. Does there exist a cheating prover that can convince the verifier? Does every cheating prover convince the verifier only with probability far away, bounded away from 1? Or is there a way to get it right? Or is there a cheating prover that can convince the verifier with very, very good probability, possibly even 1? So let's look at, let us try to be the cheating prover, and let's try to find out perm A is not equal to alpha. What can I do in order to make the verifier believe that actually perm A is equal to alpha, but so that I'm not caught in the process? So let's look at how the game is evolving. There was the original matrix A. This was an n by n matrix. This was an n by n matrix. We split. So based on the random coins, you went into one of these matrices.
Prahladh, what was the soundness definition? Could you just repeat it again? I'm just a bit confused.
Let's go to the soundness. The soundness in the case of NP was, no matter which proof you give me, the verifier should reject this one. This one says, no matter which prover you work, not necessarily a prover which behaves correctly, a prover which returns some answers, any such prover you talk with, you should accept with probability at most 1/3.
Okay.
So the question is, can we design a cheating prover that causes a verifier to accept with high probability? That's what I want to look at right now. Okay. So this is the first round. So he's picking an I in N. This is a random. I'm just drawing what are the possible random coins of this one. In the first round, the verifier is picking one of these and it's going to one of this path. Then in the next round, say it picked this guy. The next round, it's picking an I from 1 to n minus 1. So these are n-1 by n-1 matrices. It's now going to pick up some other matrix, say, which is n-2 by n-2, and eventually it will come to a 1 by 1 matrix. And the sequence, it's going to first pick I in 1 to n, then it's going to pick an I in 1 to n-1. So the actual run of the algorithm is going to follow one such path based on the random points you are doing. Now, if you are a cheating prover, how would you cheat?
I could always sort of give you, in the first case, I could give you this, that permanent of A13 is equal to alpha 3.
Yeah.
And but the others are, and that alpha is equal to A11, a permanent of A11 plus A12 permanent of A12. I can always give you this alpha such that this is true. Just because I can sort of tweak in changes in the other guys and keep and give permanent of A13 to be alpha 3.
So just restating what you stated. So if in this round, if the prover is actually going to give alpha 1, alpha 2, alpha n correctly, he's going to be caught correct right away. This check will already catch it. So if he wants to actually cheat, he has to give one of the alpha 1 to alpha n wrongly, certainly. So he'll do exactly what you do. So he's going to decide where to put the error in. One of them he's going to answer incorrectly. He's going to cheat. He could just decide to answer one of them incorrectly. He could just decide, okay, say, I am going to answer A12 wrongly. The rest I give you correctly. Now, the point is, if the verifier did not pick A12, i.e. being 2, that's it. He's gone into a path which is correct, and the verifier will just accept with correct. So the probability the verifier has to this one, the verifier should have chosen this I in the first round. In the next round, it should, once again, there is another specific round. So the prover could only commit errors on just one path. The prover could have just exactly what you said. The prover could cheat.
The prover could cheat on this orange path, but then the other blue paths, it can go correct.
And the other place is going to just cheat one of the paths. Now, what is the probability? Yeah, so now everything else it could give the correct answer. This path alone, it could cheat. So the probability that the verifier will catch the prover is only if the verifier was lucky enough that on each of these paths, it actually picked up this path. If at any point of time it deviates from this path, the verifier cannot figure out that the prover has cheated. What is the probability of this happening? It's 1 by n into 1 by n-1 into 1 by n-2, all the way up to 1 by n factorial. So the probability in this case, the probability that the verifier catches the cheating prover is 1 by n factorial. So, but the probability 1 minus 1 by n factorial, the verifier will accept. This is too close to 1. I need it to be bounded away from 1. That is, if it was inverse polynomially bounded, you could repeat it. This is inverse exponentially close to 1. So this is not good enough. So this strategy, this is certainly not an IP protocol because it is not sound. Therefore, the protocol is not sound. This protocol is not sound. This is not a sound protocol because if the distinction between yes and no is only just 1 by n factorial. This is too small.
Like the probability that it rejects is at most 1 over n factorial.
It's at most 1 over n factorial. Therefore, the probability it accepts
like
is 1.
Very low.
It's very low. It's very, very low.
Yeah.
Because you needed the probability of rejecting to be at least 2/3 for to be at least 2/3 for us. And there's no way you can amplify this also, at least using our existing response. So what we will see next time is we'll modify this. This seems as if it's doomed. There's no way to improve this. We'll actually bring in polynomials into the picture and modify it so that actually the rejection probability all the way from 1 by n factorial increases to 1 by 2 or any constant that you want. So this is what we'll do next time. Modify protocol to improve rejecting probability from 1 by n factorial to half or any constant. Okay, and that will say, it will show you, fully demonstrate how the power of IP. It shows IP is not just barely above NP. In fact, it can contain entire polynomial hierarchy. It's able to solve permanent for it. Okay. Any questions? We'll stop with this.
Just that field should be large enough means what exactly?
Field should be large enough. This is so the reason. It's just that so you're working. So it's not. I want to work in a field. So I'm not going to be computing permanent in which the entries are from GF3. GF3 is a small sized field. So I'm going to work in a field in which the field itself is larger compared to the size of the matrix. So for example, if it's an n by n matrix, so I'm going to work things modulo a prime where the prime itself is larger than 2n cubed. That's a field. Yeah.
The size of the matrix is n squared, right?
The size of the matrix is n squared.
The entries in the matrix come from
the entries in the matrix come from a field which is of large enough size.
So why 2n cube?
You will see in the proof. The next time the proof. This proof did not. Anyhow, this was an erroneous proof. Nothing happened. Next proof will come. We will be using Schwarzschild. We'll be using the degree over the field. The Schwarzschild error. We have something which I haven't. We mentioned it. We use Schwarzschild. The degree over the field, and we want this to be a small number. And the degree of the polynomials that we are looking at are something like n square. Therefore, we want the field to be significantly larger.
In Schwarzschild, we need a bigger field. That's why.
We need a field to be significantly larger than the degree. And we are going to be, the fix to today's error will be using Schwarzschild, and that will need the field to be large enough. Yeah. Any other questions?
So is there like an unbounded error kind of definition? Just you need to be greater than half and less than half. That's it.
No, but the point is because of PP, PP is already as powerful as sharp P, no?
Yes.
Therefore, you don't even need a prover in that setting.
No,
even
but like, what do you do if IP has that setting? You don't get any more power? Is that what you're saying? So
one thing which we'll later on see, which we haven't shown, is anything in IP is actually in P space. IP will, this definition of IP, which I have said, you do anything you want, define the probabilities to be any number. Whatever you do, the whole thing will be in P space. So it will never go beyond P space. And the way what you're asking is, what if I allow no gaps in this one? That is sort of like IPP or some such thing like that. We already know that even without a prover, it's all the way up to sharp P. So the question there is only a question whether, so it's even without a prover, it captures the permanent. Question is, does it capture a little more? I don't know the answer to that question.
Okay.
No, certainly it covers all the way up to P space. So I don't know if it gives you any more answer. Even bounded gives you, so unbounded also gives you.
And it will also, it will also be in P space, I guess.
It will be in P space. So this, I will do it next time. It's a very easy observation that IP is in P space.
Yeah. So then, so everything will be space.
Yeah.
Okay.
Question. Okay, you can stop the stream.